Let's wait for a couple of minutes. Then we will start. Dilip, do you have anything to say?
Yeah, I just want to ask you. I mean, are we having a instruction session today, or are we also clearing some doubts on activity questions? And...
Today is instructor session.
Okay. All right.
Sunday, Thursdays are instructor sessions.
Sure. But would we find some time to actually address any of the activity questions, just in case? I mean, in case it's relevant to understand.
At the end, we can. At the end of today's discussion, we can. If there is a time, we can discuss.
Sure. Thanks.
What question do you want me to discuss? Which question? You can tell me now. I can have a look.
See, especially activity question. Just a second. Let me just find the number and I'll let you know.
So what we are discussing today?
You will get to know it.
Activity question 3.1, question number 4.
Which week? 3.1.
3.1. That's week 3.
Okay.
First activity question set. Fourth question.
All right. So I think most of you guys have joined. So we can start now. Yeah, I will discuss your question once we are over with today's discussion.
Sure thing.
So last time, let me start with recalling what we did in the last session. So in the last time, you guys have studied about the linear combination of vectors, right? So let me start with that point. So suppose V is a vector space and V1 up to Vn are vectors in the vector space. The linear combination of these vectors with coefficients A1 up to An, which are real numbers, is going to be another vector. Right? And this is how you denote that. So this is what is called the linear combination of a vector, of collection of vectors. Now, you say a vector is a linear combination of other vectors. Okay, for example, vector V is a linear combination of other vectors V1 to Vn. If there exist some real numbers A1 to Ai, A1 to An, such that it can be written as the sum of these vectors. Okay, scalar multiple sum of these. All right. Now let's have a look at some example. So, for example, this vector in R2. All right. So this is a vector in R2. So I'm working in. So my vector space is R2. So this vector in R2 can be written as linear combination of 1, 0 and 0, 1. And what will be the coefficients? Coefficients are precisely 5 and 10. You can also have another. You can also write same vector with respect to other vectors. All right, as a linear combination of other vectors. Like
today's lecture is about week 3.
Yes. So you can write down. This vector 5, 10 also as the combination of other two vectors. All right. So the vector need not to have one combination. Okay. It can have infinitely many linear combinations. It can be expressed as infinite linear combination of. It can have infinitely many linear combination expressions. All right. This is one example. You can also think of it, writing it as 5, 10 as 5 times 1, 1, or 15 times 0.1. This is also another expression. There can be infinitely many such expressions possible for any given vector in R2. Okay, so this is what you see last time. So now it is valid to ask, when you have a vector, then how do you express that vector given as a linear combination of given two vectors? All right. So in other words, you assume that your vector, let's say 4, 3, is expressed. You need to express your 4, 3 vector in terms of vector 1, 2 and vector 3, 2. All right. So you assume that the coefficient of 1, 2 is A and the coefficient of 3, 2 is B. And now you need to find A. So how do we do that? So it is, so first you solve the equation on the right hand side. What do I mean by solving that equation? So first you need to scalar multiply this scalar with the vector. So what will you get? You will get 2A. Sorry, you will get A, 2A. Right? And when you scalar multiply V with the vector, what will you get? 3B, 2B. All right. Now, after scalar multiplication, you need to do an addition because there is addition sign in between. So you will do addition. How do you add two vectors? You add the first coordinate with first coordinate, second coordinate with second. So you will get A plus 3B, 2A plus 2B. All right. Any question till this point?
Just wanted to ask you, is it possible to break down any vector into this form? Or are there
Yes.
other conditions?
Yes. No, you can break and you can write, you can express any vector as a linear combination of other.
Okay. Thanks.
You will get to know that those special vectors are called form the basis. So you only need to know those bases, those vectors. So because you can express any other vector in terms of those vectors, so you only need to know those particular set of vectors. You don't need to know a whole vector space. You can just work with a finite number of vectors because you can express any other vector with respect to in terms of those finite number. So those set of vectors become important in order to study vector spaces because it boils down the study of whole vector space in terms of just finite number of vectors. So that will become important, and those set of vectors are called bases. So you get to know all these things in the coming weeks.
Okay.
Good
So,
question.
I haven't been able to understand the concept of these vectors too well. So please don't mind my question here. So is 1, 2, and 3, 2, are they also a part in the same vector space as 4, 3? No. Is that?
Yes, they are.
They are the same space.
They are all of the vectors are in R2.
Well, okay, because R2 is the vector space in this particular case.
Yes.
Okay.
Sir,
Because in some cases they define them as V, right? I mean, so in that case, if it's specifically defined, then we have to.
Yeah. So in this case, So in this case, your vector space V is R2.
Okay.
I'm working with vectors in R2. Yeah.
All
Our vector space is R2.
Okay. Thank you.
Sir, how did you get 4, 3 and this 1, 2 and 3, 4? Is it we subtracted it or something like that?
No, this is given to you. So you want to express vector 4, 3 in terms of as a linear combination of vector 1, 2 and 3. That's the question.
Sir, I mean, if you can just explain what is basically a linear combination is all about.
That we have discussed. This is what I'm recalling now.
Okay.
You guys have discussed this already in the last session.
Okay.
I'm recalling this. I'm not teaching this. And this is not new to you. It is not supposed to be new to you because this has already been covered in the last session.
Okay, sure.
Yeah. So now we want to find out A and B. So right hand side you have solved to this point, and the left hand side is 4. All right. Now how do you compare two vectors? In R2, first coordinate must be equal to the first coordinate, second coordinate must be equal to the second coordinate. So if you write down these equations, how many equations will you get?
2.
Yes. So what is the first equation? First equation is 3AB plus A plus 3B is equal to 4. Second equation is 2A plus 2B is equal to 3. Now, does these two equations look familiar to you? Whatever you have studied in the first 2 weeks of session.
Yes.
This restriction session. So what are these two?
Sir,
These
actually, in
are-
first 2 weeks of this, we have covered the vector space. I believe Lavanya madam has taken that class where majorly vector space were discussed.
I think you were not there. I took the classes in first 2 weeks. Lavanya took the last session. I don't know what we are talking about.
Okay, sure.
And I covered a system of linear equation. I discussed about how to form a vector. I started with vectors and matrices. Okay, but whatever it is, this you have already seen.
Is
So
this a
you
linear
want to answer
equation
that, or you
system?
want to discuss me about the thing? So it's better if
Linear
you
equation
discuss.
in two variable.
Linear equation
Yes.
system?
Right. It is a system of linear equation with two variables. That is correct. So this is what you have seen already. So I would suggest you guys, instead of arguing with me, it's better if you can discuss whatever I'm asking. Okay, so this becomes a system of linear equation. Now we have also discussed how many ways. We have also discussed some ways to solve a system of linear equation, right? So if it has two equations and two variables, in this case it has two equations and two variables. And what is the coefficient matrix corresponding to it? It is 1, 3, 2, 2, right?
Yes.
And A, B, and the right hand column will be 4, 4. Right? This is what we have already discussed. Now, yeah, so this is your coefficient matrix. Now it is matter of solving this coefficient. Okay, how do we solve this coefficient matrix? So now, because it has two equations, two variables, so you can use, there were two methods that we discussed for such system. So first we need to check whether the coefficient matrix has determinant to be non-zero or not. So what's the determinant of this? If it has not determinant to be non-zero,
Minus
what's the
4.
determinant of this? -4. So it is non-zero. So what are the two methods that we discussed to solve such type of system?
Kramer's rule.
Kramer's
and,
rule.
Right. So
Rowe-Eklund
there was
form.
Kramer's rule, and then
Invertible.
yeah, invertible
Rowe-Eklund.
matrix. Rowe-Eklund is also Rowe-Eklund is for general. You can apply Rowe-Eklund form to invertible. Right. So you can use either of that, or you can use the general method, which is Rowe-Eklund. Right. Okay. So now I will. So these two things are computational. These first two things are computational. So let's start with Rowe-Eklund. Okay. So now let's perform Rowe-Eklund. Let's perform the row operations one. So it is 1, 3, 2, 2. All right. So first we need to write down the augmented matrix. So augmented matrix is this. Now we want to convert the coefficient matrix into a row echelon form. So now what will be your operation? So I will apply first R2 minus 2R1. All right. So 0 and minus 4. 3 minus 8 minus 5. All right. Now I will divide R2 by
-4.
or I will multiply R2 by minus 1 by 4. And this will give me
1.
1, 3, 0, 1. 4 minus 5, 5 by 4. Right? So now then we saw that there are two independent dependent variables. So in this case, the leading terms are called the dependent variables. Right? Do you guys recall that?
Yes, sir.
The leading terms are the dependent variables. Right? Now you can express your dependent variables directly. Now in this case, there is no independent variable. All right, because independent variables are those which are not dependent. But in this case, there is no independent variable. So what is your B? So now write it back into the form like this, 5 by 4. All right. Now, what is your A? A is 3. A plus 3B is equal to 4. And your B is 5 by 4. Now, once you know B, you can apply it in the first equation and you can obtain A. So, A is 4 minus 3B. Right? Which is what? Which is 16 minus 15, 1 by 2. All right. So now A is 1 by 4, B is 5 by 4. So you have found out that 4 by 3 is equal to 1 by 4 of half, 1 by 2, and 3 by 4 of 3 by 2. Now, can you check also? Can you verify this as well?
Sir,
So it is,
sir, I have doubt which variable we say as independent variable.
wait, there is a, it is 5 by 4. Just a second. Yeah, the leading terms in your Russian forms are called the dependent variables. Okay, so you know, so after performing row operations, you will get leading terms, right?
Yes, sir.
Each row will have leading term. So that leading term will corresponding to that vector, corresponding to that variable. So each column will have a leading term. So corresponding to that column, there will be some variable. So those variables will be called dependents, and other variables which are not dependent, those are called independent. Okay.
Okay, but it should be leading only.
Yeah.
Okay, sir.
So this is, you can verify also. This is what. So this is how you can write. You can express any vector in terms of other vectors. All right. By solving this system of equations. Okay. So now you guys have also seen the concept of linear dependency in R2. Okay. In the last session, we have discussed the linear dependency of in the case of R2. Okay. So in general also, a set of vectors v1 up to vn form a vector space. From a vector space, we are said to be linearly dependent if there is a scalar, if there exist scalars a1 up to an, which not all of them are 0. So there has to be some non-zero coefficient also, such that this combination is equal to 0. So that the linear combination of these vectors with respect to these coefficients is equal to 0. Okay.
Sir, I have a doubt.
Yes.
Sir, means some coefficients are 0, right?
No, this doesn't. It doesn't say this. It says not all coefficients are. It just says that. It doesn't say that some coefficients are. It doesn't say.
Okay.
Okay. So this is the definition. This definition. Let's look at some example.
Do all these
Let's
coefficients?
look at some.
May I ask a question?
Yeah, please.
So all these coefficients are they coming from the linear equations which have n?
No. These are
variables?
scalars. A1, A2, An are scalars.
Scalars. Okay.
Okay, so you don't get confused with this. So in order to solve this, we use system of linear equation. Okay, to find out these AV. But these AVs were scalars. Okay, so you are pointing to the correct thing, but so in order to solve this, in order to find out whether the vectors are dependent or not, we will use system of linear equations because it will turn out to be a system of linear equation, and in that case, these scalars will become the variables.
Okay. The scalars is what
In
we
that-
found by breaking down the vector, right? The 4 and 3 sometime back when we got a and b from the from the vector that was 4 3. Yeah.
No. Scalars AB were these were their scales, A and B.
Yeah. Okay.
Yeah. So set of vectors are called linearly independent if there exist scalars A1 to An, not all of them are 0, and they satisfy this equation. That means what? That means the linear combination of V1 and Vn is 0. And the coefficient in that linear combination, not all of them are 0. It may be possible that some of them are 0, but not all of them are 0. But it doesn't say that some of them will always be 0. There can be case that vectors are, scalars are non-zero. Let us look at this example. This definition might be confusing at the first instance. So let us look at some example. So now question is, are these two vectors find out if vectors are linearly dependent or not. All right. So let's look at this example 4, 5, and 1 by 4 and 1 by 5. So what you need to do, you need to find out 4 and 5. You need to find out the scalar. So that AB suppose for some AB, this is equal to 0, 0, 1. All right. So now you need to say, now you need to find out that there is a solution to this equation where not A and not both of them are 0. Okay. So again, it will become a system of equation, linear equation. B by 4 equal to 0. 5A B by 5 equal to 0. All right. Now, if you solve this, what will you get? So how do you solve that? You multiply 4 times this and 5 times this. Okay. So what will this give us? This will give us 20A plus 5B by 4, 20A plus 4B by 5. All right. Now, you subtract these two equations. So what will you get? This will cancel out. So you will be left with 25. You will be left with 5B by 4 minus 4B by 5 equal to 0. That means 20, 25B minus 16. That means 9B by 20, that is equal to 0. This implies B is. All right. Now, if B is 0, then what is A? Does A also 0? So now let's take this equation first. Okay. So now let's take this equation over here. So we have 4A plus B by 4 equal to 0. Now you have find out that B is 0. So 4A is equal to 0, implying A is also 0. So A and B both turn out to be 0. Okay. And what was the condition over here? Not all of them are 0. Look at this picture, not all of them. So that means there is no combination of these two vectors in which A and B, no combination of these two vectors expressing 0 vector where the coefficients are non-zero. Either of the coefficient is non-zero. Okay. So both of the coefficients turn out to be 0. So there is a unique solution to this. And so these two vectors are not dependent. So these two vectors are not dependent.
But sir, again, in case if we are say for B, we are taking it for 0, right? So in that case, every equation will be like this only, right?
No, we are not taking it to be 0. We are finding out it is 0.
Correct. So, but
I'm not taking it.
We are equating the equation with 0 only, right? So in any case,
yeah, because it is a 0 vector. Because I'm saying that this is the definition. It should be equal to a 0 vector. So that's why I'm equating it to 0 vector.
No,
right?
my doubt is if we are equating it to 0, then most of the equations will become 0 only, right?
No. It will not. I will give you an example.
Okay.
Yeah. So now let's look at this example. Do you think the same will happen to this, Vipul?
Pardon me, sir?
Do you think the same will happen to this set of vectors also?
Yes.
Okay, let's see. So again, we need to check whether these two vectors are independent or dependent. We need to check whether these two vectors are dependent. So now again, write down their combination equal to 0 vector. All right. Now we need to find out A and B. Okay, and not both of them should be 0. That is what the condition in order to say that they are dependent. So solve them. So we will get 3A plus 2B, all right, equal to 0, minus 3A minus 2B equal to 0. All right. So you can just add these two equations. All right. So you can see that the second equation is the minus 1 time multiple of the first equation. Okay. And if you add these two equations, you are not going anywhere. So these two equations are same as having just one equation. Do you see the point? Having these two equations does not give you any additional information. Okay. It is just saying that the second equation is just 1 minus 1 multiple of the first equation. So it is not giving you anything additional information to find out the variable A and B. So both equations are just one single equation. So it is sufficient to consider only one equation. And now you can express A in terms of B. So what is A? A is basically 2 minus 2 by 3. And your B can be anything. B is any real. Okay. So how about if I write down this system, this homogeneous system of equation in terms of your known row echelon form? So you guys are already familiar with this thing. So let me write down it in the augmented matrix form. So what is the augmented matrix of this? Augmented matrix will look like this, right? Now, what is the row operation that you will perform on this in order to get the row echelon form? R2 plus R1, right? You will change your R2 by adding R1. So what will you get? You will get 2, 3, 0, 0. All right. And then you can, in order to get the leading term to be 1, you can divide R3 or you can divide R1 by 3. So you will get 1, 2 by 3, 0, 0, 0. All right. So now what you see that how many leading terms are there? There is only one leading term. And how many? And in the second row there is no leading term. So the second variable corresponding to the second column is the independent variable. Okay. So that is what. So that means this is the leading term. So this will give us A to B, the independent variable. And because there is no leading term, so it implies that B is independent variable. All right. So, and that is what is happening. If you look at the case here, so A is expressed in terms of, that means, and B is the independent number. So that is what. So these things are all same. Either you do this way or that way. But yeah, I should not say you should do this way, because in 2x2 these things are doing this way are simpler, but this is the standard way. So I will always, so yeah, so you need to do in this way. But
that
yeah,
means
so I'm just trying.
we have infinite solution over here.
Exactly. We have infinitely many solutions. And if you take your B to be some non-zero number, okay, so if you take your B to be 1, then you can have A to be minus 2 by 3. Correct? So not both of them. So neither of them is 0 in this case. So you can express 0, 0 in these two terms with non-zero coefficients. Okay. So what does it say? It says that they are dependent. They are linearly dependent.
So,
Alright.
so it just means they are on the same line, right? If you draw.
Yes, in R2, it just means that. Yeah. Can anyone tell you what is that line? If you guys going there, can anyone tell me what is that line?
Which one, sir?
So as Dilip pointed out that it is a line. Both vectors are in a line. So can anyone tell you what is that line?
Minus y?
Y is equal to minus x?
Y is equal to minus x. Yes. That is it.
Sir, how?
Minus y.
Basically, x is equal to minus y.
Yeah, that is what the equation is. So you look at the coordinates. So it is first coordinate is x, second coordinate is y. And what do you notice over here? That the y coordinate is equal to minus of x. That is the answer. But there are other ways also, because now you can also see, because there are 2 points which looks like they lie in the same point because they are dependent. So you know they are. Yeah, I will come to that. Okay, so it is not important right now. But yeah, okay. So now what about these two vectors? Again, for these two vectors also, we will do the same exercise. So 1, 3, 4, a times this plus b times this, and we will equate it to a zero vector, but in R3, because these two vectors lie in R3. So we will equate it to zero vector in R3. So again, we will get two set of equations, a plus 3, a plus. So we will get a plus 4b equal to 0, 3a plus 3b equal to 0, 4a plus b. Okay. So it is, what kind of system is this? It has two variable, but two variable, three equations. Okay. So what is the corresponding coefficient matrix? If you look at the coefficient matrix, it will be of order, anyone, 3 cross 2 or 2 cross 3?
3 cross 2.
3 cross 2.
3 cross 2. Right. So 1, 4, 3, 3, 4, 1. Right. Now we just need to find out whether it is a combination. We just need to solve the system and find out the values of AB. If there are infinitely many solutions are there, then it is dependent. And if there is only unique solution, that means A and B has to be 0. Both of them has to be 0. Then it is then they are not dependent. So yeah, I'll just leave it to you guys so this is exercise for you to complete. Okay, the same thing we will do here. All right. Now look at this.
Sir?
These three. Yeah.
So can we first solve the two equations and find the value of a, b? By this, can't we?
Okay. Yeah, you can also do that. That is also
As
good.
it is coming
You can
a0 and b0, so it is not dependent. By solving
No, but
the first
whatever
equation.
solution you get over here in the first equation, that also needs to satisfy the third equation. That is the thing.
Yeah, it is satisfying.
So what
0,
solution
0.
you are getting? 0, 0.
0, 0.
Right. Okay. Yeah. So that means A and B both are 0, 0. That's the only solution. That is what you are saying.
Yes, sir.
Yeah, that is also there. So that means, are they independent or independent? Are they dependent or not? Yeah, they are not dependent. They are not dependent, right? Right. Now look at this. Now look at these three set of vectors. Again, now what you can notice here is that. So again, you have 1, 2, 3.
3 variable, 3 equation.
Right, 3 variable, 3 equation. So let's use A1, A2, A3 equal to 0, 0, 0. All right. So you will have 3 equation, 3 variable. You can again solve this and you can find out A1, A2, A3. All right. But what will you notice here? That they are dependent. All right. And in particular, if you add, so in particular, A1 is A is 1, A3 is A2 is 0, and A3 is no, sorry, A1, A2 is also 1, A3 is also 1, minus sorry. Right. So it is this. Yeah. A1 is minus 1, A2 and A3 are 1. So that means minus of this. So this is what I'm giving you. So just think of it as an exercise again. And the answer is this. They are dependent. And look at this.
Can sir, a value of A1, A2, A3 we can also change?
In this case?
Yes, sir.
Yeah, you can take any multiple of this vector.
Okay, sir.
What do I mean by that? You can also take minus 2, 2, 2, or minus 3, 3, 3, something like that.
Okay, sir.
Right? That will work. So this is just one choice I'm giving. Okay. So what happens over here is that, yeah, you can verify that this sum of these 3 vectors will be equal to 0. Now you can also think of it as like this, that this sum of the last 2 vectors, you can take 1, 2, 3 on the right hand side. So you will get 1, 2, 3. Right? So these 2 things are same. You can take it on the right hand side. So in other words, if 3 vectors are dependent, okay, so you can write one of the vector in terms of the other 2. Okay. If 3 vectors in R3, so let me be precise. If 3 vectors in R3, these 3 vectors. So what you have noticed over there is that if 3 vectors V1, V2, and V3 are dependent in R3, then one vector is a linear combination of other 2 vectors. All right, as you have noticed in this case. Okay. All right. Now, what about this superset? So you have noticed that these 3 vectors are dependent. So yeah, so these 3 vectors are dependent that we have seen, and we have also noticed this small remark. Now, what about this superset? What do I mean by superset? This set of 4 vectors already contains last 3 vectors that you consider. So what about these 3 vectors? Can you say that they are dependent or they are not dependent? Can you say anything?
They are dependent.
Okay. Can you explain why? Yeah, you have said correctly. Yeah, they are dependent. Yeah.
If
Please.
one of them, if 3 of them is dependent, then any superset also dependent.
Right.
Can I explain, sir?
Yeah, please.
Because the last term we can take 0, and other
Exactly.
3 will remain and it will become dependent.
Right. Exactly. So we already know that first 3 vectors of this set are dependent, right? And this is the new entry. So we can just take the coefficient of this to be 0. Okay. And we will get 0 vector. So we can express 0 vector as a linear combination of the all 4 vectors, where the coefficient of the last or newly added vector will be 0. So in other words, more precisely, so in other words, more generally, what we can say is that if a set is linearly dependent, then so is every superset of it. So in the previous example, what I have said is 1, 2, 3 minus 1 of 1, 2, 3 plus 1 of minus 1, 0, 1 plus 1, 2, 2, 2 plus 0 times 4, 3, 1 is equal to 0. So notice that not all of the coefficients are 0. Okay. So it satisfies that condition also. And their combination is equal to 0. Okay,
So
they are
2 vectors
dependent.
need to satisfy the condition. Beyond that, everyone else can have a 0 coefficient.
Yeah. So the condition only says that not all coefficients are 0. So
even one is non-zero and then rest can be 0 in some condition.
no, but that will not. So suppose if you take 1 to be non-zero, let's say k is non-zero of some vector. Okay. Let's say a. Let's say 1, 2, 3. Okay. Let's say k is non-zero. Let's say 2, and then other vectors are, let's say 0. But then
it cannot become
force you,
0 vector.
Yeah,
Yeah.
it will force you to have that coefficient also known to be 0. So
Yes, so one more vector has to be there.
one more vector. So Dilip has correctly pointed that out.
Sir, excuse me, sir.
Yeah, please.
Sir, 4 vectors in R cube will always be dependent, no?
Yes, I will come back. You are correct.
Sir, can you explain this again?
Explain what? Superset?
Yeah.
Right. So I already have 3 vectors to be dependent. So you understood this point, right? That first 3 vectors of this set is dependent, right? Now I have added one new vector to it, right? So now look at the combination. So if I write down the combination, I need to express 0 vector in terms of these 4 vectors. Not all of the coefficients should be 0. So I can take the last vector's coefficient to be 0. So this doesn't matter anymore. Only the last 3 vectors will matter. And we already know they are dependent. So,
Okay.
So that's all. So we will get the new superset also being dependent. So in particular, you can generalize this argument to say that if a set is linearly dependent, then so is every superset. Okay. Now, what is linearly independent? Okay. So if a set of vectors are not dependent, then it is called linearly independent. Okay. It is just negation of dependency. So we noticed over here a few collection of vectors which were not dependent. Okay, so those becomes independent. For example, someone noticed that these 2 vectors were independent. All right. So someone noticed that these 2 vectors are not dependent. So these 2 vectors becomes independent in R3. Similarly, we noticed that the very first example of ours, these 2 vectors in R2 had only unique solution, which is 0, 0. Okay. So these 2 vectors also become linearly independent. All right. So whenever you have collection of vectors which are not dependent, then they are independent. So what we have noticed from this example, we noticed that if you are in the setup of 2 equation, 2 variable like thing, n equation, n variable, then you will work with this homogeneous system. Okay, because we need to check what dependency. So you will work with this homogeneous system. You will get this homogeneous system of equation, right? And now, if the homogeneous system of equation has a unique solution, that means 0, 0, then they are linearly independent. Okay, this is what we have. We can also take from this. I will repeat. If you have two vectors and you are checking for the linearly dependence, then you will try to solve this equation. Okay, and you notice that because there are two variables, and there are two equations also. So it is an equation and variable type thing. You perform your row operations and you find out that this homogeneous system of equation has a unique solution. That means if it has a unique solution, it just simply means that the vectors will be independent, because they cannot be dependent, because both of the coefficients will become 0. So they have to be independent, because they are not dependent, so they are independent. So from this, one can also write down an equivalent definition of linearly independent in terms of the linear combination. Suppose you have a set of vectors v1 to vn from a vector space. So these set of vectors are called linearly independent if their linear combination is equal to 0. Okay. So I assume that their linear combination is equal to 0, satisfies only one equation, one solution, that all of the scalar coefficients are 0. There is no other solution. Okay. So if I start with this condition, that if I consider a linear combination of vectors v1 to vn, linear combination of these vectors which expresses 0, then all the coefficient has to be 0. Then I will say that my vectors v1 to vn are linearly independent. Okay. So notice that is what we did in our example. So for example, in this case also, we expressed 0 as a linear combination of these two vectors. We solved our system of equation and we find out that the only solution is there is a equal to 0 and b is equal to 0, making vectors to be independent. Similarly, in the first case itself, we did the same thing. We started with two vectors, okay, and then we write it as a linear combination of 0, and then we found out after solving the system equation that the only solution it has is the 0.
Sir, why did you call it a superset?
Which one? Superset is gone long back. This superset.
Why did you name
there is
it?
Subset. There is subset, and then there is superset. Superset means it is bigger than your set. That's why superset. Okay. Sub means it is part of your set. So it is subset.
So it will be having a rank 3 now.
What is rank?
So when we zero, when we have all the zeros eliminated, get all the zeros, the remaining residue which is left, we call it rank. That thing.
I'm okay. So remaining.
Sir, remaining
in what?
Sir, in rows, say when we eliminate, we have 3 by suppose.
Okay, so what you are trying to say, I think.
Yes, sir.
You are right. You are trying to say write down the coefficient matrix.
Yes, sir.
So it will correspond to 4 rows, and then you will perform row operation on this.
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
3 rows back, and other 1 row.
Yes, sir. Last row will be 0, 0 something.
Right. So yeah, but we haven't discussed that. So let's not go into that.
Okay.
Yeah.
Sir.
Yes.
So can 0 vector be an element of superset?
Anything can be element of superset.
Okay, sir. So can we say that to be linearly dependent, there must be the 2 variables which are non-zero?
What do you mean by that?
Means that to become the linearly dependent, the 2 variable a b, let we have a b c d multiplying, they are the coefficients. So there must be any 2 variables which are non-zero to be linearly dependent.
Yes, that is what the definition of linear dependence.
But if we take a 0 vector and other vectors, but and the coefficient of the zero vector can be anything, and remaining the zero vector, the coefficients of other vectors we take as zero, then it also forms the linearly dependent.
Yes.
So can we say that one can also satisfy, if one element, if one coefficient of any one vector is also not equal to zero, then also we can say that it is linearly dependent.
No. So linear dependency, you need to have not all the coefficients can be zero. That is the definition. In your definition also, in both of the cases, there are vectors with non-zero coefficients. So what is the problem? I don't understand.
सर यदि हम लोग एक
the definition of dependency.
यस सर, जैसे हम लोग एक वेक्टर लेते हैं 0,0,0, उसकी जो कोफिशिएंट्स हैं हम लोग कोई भी ले सकते हैं 1 2 3 4, और जो अदर जो वेक्टर्स हैं उन सब के कोफिशिएंट्स हम लोग ले लेते हैं 0, तब भी तो ये लीनियर डिपेंडेंट कहलाएगा। तो मतलब हम लोग ये नहीं कह सकते ना कि दो वेरिएबल का दो कोफिशिएंट्स नॉन जीरो होने ही होने चाहिए।
Oh, like that version. Okay. Yeah, if you're comparing with zero vector,
yes sir,
then they are always dependent with zero vector. Anything is dependent to zero.
Okay sir.
If you add zero vector, then right. But what we were discussing, if you have non-zero vectors and then you are finding out, then you need minimum 2. That is what the earlier discussion.
Yes. Okay, sir.
Okay. Yeah. If you add zero vector, if you already have a zero vector in your set, then zero vector is expressed as a zero vector. So you can take other coordinates to be zero, but zero vector coefficients to be anything. So that set will be dependent.
Yes, sir. Thank you, sir.
That is why we really do this. Okay, good. So now, so equivalently, when it is not dependent, so it is linearly independent, and this is what that equation will become. So we will start with the linear equation. We will start with this linear combination of 0 in terms of v1 and vn, and you will find out that the solution of this thing, that all the coefficients are precisely 0. So let's take this example. So 1 0 and 3 0. So if you write down 1 0, you take the linear combination of this, equate it to 0, you will get a plus 3b equal to 0, and second equation will be 3b equal to 0. Now this implies that b is equal to 0, and if you place b back into the first equation, you will get a also equal to 0. So it has unique solution where a and b both are equal to 0. So these are. So what is this? This is linear independent.
Sir, can you please scroll up?
Independent. Sorry, can you say that again?
Can you please scroll up, sir? So that line, that a set of vectors v1, v2, vn. Yes.
Yeah, you will get notes, so you don't need to copyright. Let me finish. You will get notes. Don't worry. Okay, so this
Last
second
line,
example.
sir.
Sorry.
Last line left. This after satisfying.
You will get notes. You will get notes. Don't worry. Yeah, please focus on the lecture. Don't focus on writing things down. Okay, it will be better. You will get everything written down. Whatever I'm writing, you will get as it is. Okay, plus something new added, not anything less. All right. So let's consider these two vectors. So can anyone tell you whether these two vectors are independent or not? Okay, so I allow you to use your brain and copy pen, whatever you want. Just tell me whether these vectors are independent.
They are independent, sir.
They are independent. Okay. What about others?
Yes, sir, they are independent.
Okay.
Independent.
Out of 40, at least 5 people should say
independent.
Yeah. I can ask why they are independent also. So you need to prepare with your proper session. So just not listen to others and just yell in confusion.
Yes,
One
sir,
more
they are
guide.
independent.
Okay. Okay, so for those who haven't solved this, this is an exercise to check if they are independent. All right. Now, this is also one of the another equivalent notion that V1, V2, Vn are said to be linearly independent if only the linear combination which is equal to 0 is the linear combination with all coefficients. Okay, so it is just a rephrasing of whatever we said earlier. It's nothing much. Right. Now, as I mentioned earlier that three vectors are linearly dependent if and only one vector can be written as the combination of other two vectors. Similarly, if you have two vectors, which are linearly dependent, then one of the vector has to be a multiple of the other vector. Okay. So as you have noticed earlier, so let me go back to the examples of the previous cases where we considered a few dependent cases. So let's look at this example. Okay, -3, -3, 2, -2. So what is the combination? What is so as you notice that you can write, if you take B to be 1 and you can take A to be -2/3, you can write down your first vector in terms of the second vector. Okay, so let me just copy it from here and then paste it over there so that it will be 0. Right. So now let's look at this example. Okay. Yes. Right. So let me remove all these things because we have already seen these things. We already know the solution. So all right. So we know they are linearly dependent. And what is the combination? B equal to 1 and A equal to -2/3. So if you use this combination, what you can express, you can write -2/3, 3, -3 plus 2 -2 equal to 0, 0. Now you can take this, or you can take it over there on the right hand side. And what will you get? You will get 2 -2 is nothing but 2 times 2/3 times -3, -3. So what you are seeing over here is that if two vectors, we started with two vectors which were linearly independent, and we find out that the one of the vector, one of the vector is the scalar multiple of the other. Okay. So, or moreover, suppose you have two vectors. So in general also, if you start, let's say, vector v1 and vector v2 in some vector space V are linearly dependent, then v1 a v1 plus b v2 equal to 0, right? Some 0 vector. So this 0 means a 0 vector. So now you can express, now since one of them, since they are linearly dependent, so one of them has to be non-zero. Either A or B has to be non-zero. So you can express, suppose A is non-zero, then you can express your B2, you can divide the whole equation by A because it is non-zero, and you can express V1 as minus V by V2. All right. So what is the takeaway from this? That if two vectors are linearly independent, if and only one vector is multiple of the other. So this is shorthand notation for if and only, which means that these two statements are equivalent. So two vectors v1 and v2 are independent if and only one vector is a multiple of the other. So this is for example, and this is the general argument. All right. Now we have already noticed that if three vectors are linearly independent, if and only if one vector can be written as the linear combination of the two vectors. So let me take that example from the top to the bottom. So this is the example that we saw. We take this over here. Paste it over there. All right. That's good. This. So this is for example, and you can express we are one vector in terms of the other vectors. Okay. So or in general, suppose v1, v2, and v3 are three vectors in your some vector space P, such that they are independent, they are dependent, then you have this combination written where suppose one of them has to be non-zero. So I assume that A1 is non-zero. Okay. So now again you can divide by A1 because it is non-zero, and you can express your V1 in terms of the other two vectors by taking them on the right hand. All right. So you can express your V1 in terms of other vectors. So this is what happens in general. All right. So similarly, if you have n vectors, okay, in some in Rm, let's say, which are linearly independent, suppose they are linearly independent, then they will correspond to some system of equation. So in other words, you will start with looking at this combination of these vector, which equates to zero vector. Okay, and this will give you a system of equations. Okay, now since these vectors are sitting in Rm and they are n vectors, so can anyone tell me how many equations we will get?
M
N
equation.
equation.
Right, we will get m equations. So the corresponding matrix. So in particular, your typical Vi will have m many coordinates. Okay, so let me just write down it in this way: Vi1, Vi2, up to Vi. Okay, because it is a vector in R. So it will have. So you can expand all these things, and you will get a system of equation which will look like this. So A1, V1, V11 plus A2, V12 up to Right. A1 V1 1 plus A2 V2 1. So let me change this notation. Let's take 1i, 2i, mi. Now it looks better because it has m equations. Yeah. Now it makes sense. So the notation will change. After notation change, it will become 1, 2 up to a and b 1n, and it has m equation, so it will have this. This is equal to 0. A 1 b what is this? This will be m1 a2 bm2 up to a n bmn equal to 0. And if you write down the coefficient matrix of this system of equations, so this becomes a homogeneous system of equation. So this is what? This is an homogeneous system of equation, and you have already seen this homogeneous system of linear equations. Okay, and you have already seen this, how to solve this system of equation. Okay, so now, right.
Sir, can you explain? Sir, can you explain how you got the equations? Like I'm confusing with A1 subscripts. I'm confusing with actually.
So you write down. So you understood this. I'm expressing V1 in terms of this vector. Is this part clear to you?
V1 in terms
because each Vi is in Rm. Okay. So how many coordinates will it have? It will have m many coordinates, right?
Yes. Yes.
Is that part clear to you?
Yes.
So I'm just writing my vector Vi in terms of, so there will be m many scalars, right? So these are the coordinates, first coordinate, second coordinate, m coordinate. Got it? And this I tells you that I'm expressing my ith vector. That is what it tells. Right.
But how
now
do you
write down this?
Sorry, how do you get m equations?
Yeah. So now you write down this vector back into this equation. Okay, write down in your notebook. So you write down this vector back into this equation, each of the vector. Okay. So for example, let's take simpler cases. We have already seen. Okay, so let me go instead of down upwards. So go downwards. So for example, there are two vectors like this in R2. Okay. So then how will you write it down? A1 1 0 2 plus A2 3 3 5. Now how many equations will be there?
2. Okay, I get it now.
2. How many equations? It's not 2.
So, but in R2 can be only 2 coordinates, right? It can
Oh,
be...
sorry. Oh, okay. Sorry, my bad. Sorry. 3 and R. Obviously, these vectors are in R. Sorry. Yeah. How many equations will be there?
3.
But even in R3, here you will only get 3, right? 2, right?
Equations. How many equations will you?
We need 3 equations.
3 equations.
3 equations. Right.
Yes.
Do you see now? 3?
Yes, I
First
see it.
equation.
I see it. Yeah.
Second equation will be just 3a2. Third equation will be just 2a1 plus 5a2. And then you have 0 0 0 on the right hand side. So you will equate to 0 0 0 in order to get the system equation. So we have 3 equations, right? So similarly, when you have vectors in Rn, how many equations do you expect to get? M, right?
Yes.
It is the same generalization, nothing much. Okay. So you get a homogeneous system of equation with n variables, but m equations. Okay. Why n variables? Because there were n vectors. Why m variables? Because we took vectors from Rn. Okay. So we get this system of equation, homogeneous system of equation, and now we know how to solve this. We will write down the augmented matrix. We will perform the row operations. We will get the row echelon form of the quotient matrix, and then we will get the number of dependent and independent variables and so on. Now, when the system is independent, so when you are looking at the vectors, when you're looking at the collection of vectors and they are independent, then the only solution that is possible to this is the zero solution. Okay, by definition, it should only have zero solution. It cannot have any other solution. Otherwise, they will become dependent. So if it has a unique solution, which is the zero solution, in those cases, it will be, if the system of homogeneous system of equation has a unique solution, in those cases, those vectors will be independent. So if above system has a unique solution, that is 0, 0, 0 vector in Rm, then what? Then vectors v1, vn are linearly independent. All right. So we have, so this becomes the condition for linear independency in the case of m, where n variable m equations. Right. Now, look at this example. So, so is everyone comfortable with this part? Whatever I discussed, I haven't discussed anything new. It just whatever you knew, I just reformatted in this setup. Okay. Good. So now let us look at this example. So again, there are two vectors and they are in R3. So we will solve the system of equation. And if it has unique solution, then they are independent. But clearly, because there are two vectors, so we know if there are two vectors, if they are dependent, then they have to be combination of each other. Linear, they have to be multiple of each other. Right? That is what we notice earlier. So can you tell me quickly whether they are multiple of each other or not?
No.
No.
Right. Yes. So why? Where is the problem? Why they are not the multiple? Can you quickly tell me that?
There is a 0 in the middle.
Yes. So if you take 0 over here, multiply 0 with the second vector, all other entries should be 0. Right. So in order to obtain 0, so it needs to multiply it with 0. Yeah, correct. You get the point?
But
So,
all are multiples. Huh?
Right. So suppose this vector is a multiple of 3, 3, 5. Right. Then what does the second equation say? Second equation says that 3k has to be equal to 0, which implies that k has to be equal to 0. But if k is equal to 0, then you will get a 0 vector. And the vector that we are comparing with is not a 0 vector. So that means they are not, you cannot write one vector in terms of the other vector as a multiple of the other vector, which means they are not dependent, which means they are independent. You get that?
Isn't it necessary that all should be a multiple of the second one?
In case of two vectors, yes. That is what we just saw, right? If you have two vectors which are dependent, then you can write one vector as a scalar multiple of the other. All right. So that means these vectors are linearly independent. So you don't need to solve the system of equation. You can just directly get this.
Sir, is that all?
Now, what?
Sir, if we can't express in terms of multiple of other two vectors, we can directly tell they are linear. They are not dependent.
Can you completely say the sentence?
No,
What is the hypothesis?
What I'm
What is
asking
the hypothesis?
What I'm asking is if one vector can't be defined as a multiple of other vector,
yes,
we directly tell without any computation they are linearly independent.
Yes.
We no need to do any.
You are doing computation, right? This is your computation. Because if they are multiple of each other, that means you can express, there is some k, you can express it in this way, then which will force that k has to be 0 in this case.
Okay.
Because, right, this is the computation that you are doing. You are not doing this linear computation, but you are doing a smaller computation.
Okay, sir.
Got it?
Okay, sir. Yes, sir.
Yeah, but this is only applicable when you have two vectors.
Okay.
In case of three vectors, if you can express one vector in terms of other two vectors as a linear combination of other two vectors, then they are dependent. And if you can't do that, then they are independent. Okay. Now, what about in this case? Are these vectors independent or dependent?
Dependent.
Dependent.
Dependent. Okay.
Dependent.
Can anyone tell me why? Why?
Sir, any vector in a plane can be expressed as the linear combination of other two vectors if they are not collinear.
If they are not, even if collinear also. Achha, the other two vectors are not collinear. That's what you mean?
Yes, sir. The third vector can be expressed in terms of the
Right.
other two
That
vectors.
is true. That is true. That is true. Now let us look at why it is. So if you express, let's say A1, A2, A3 equal to 0, 0. All right. So now it will give you how many equations? It will give you three equations. Sorry, it will give you two equations, but three values. Right. So it has, so M is 2, N is 3. So
Unique solution.
Huh?
Unique solution.
Sorry. It has unique solution. No, if it has unique solution, then they have to be independent, right?
It has infinitely many solutions.
Yes, it is infinitely many solutions. Why?
Because there are less
Why?
equations and more variables. So one will be always
Yes.
dependent on the others.
Yes, yes. So one variable will always be independent in this case. If you write down the row echelon form, and if you try to solve 2, 3, 3, and if you solve this system of equation, this augmented matrix, and you convert this into row echelon form, right? So what you will get that it can maximum have two leading terms, right? How many leading terms it can have? Leading variable, leading entry.
2.
How many leading entries it can have? 2. Okay, it cannot have 3 because there is no third row to have the third leading entry. But how many variables are there? There are 3 variables, right? So what it means that there will always be one variable which is independent. Okay. So whenever the number of equations are lesser than the number of variables. Okay. Whenever the number of equations are lesser than the number of variables, then what happens? There will always be an independent variable. Okay? There will always be an independent variable. All right. And what it means that whenever you have independent variable, it means you have infinitely many solutions. Okay. That is what we have noticed. So in other words, that is, there are infinite solutions. So this system solution. All right. So it has infinitely many solutions. Okay. Because it can only have two maximum leading terms. And there are three variables. So one variable will always be independent. Okay. In generality, this is what happens. And hence, there it has infinitely many solutions. So, yeah, in the case of homogeneous system, I'm talking about. It is in heterogeneous system. In the case of non-homogeneous system, the solution set may be inconsistent. Okay, so we don't know about that, but for homogeneous system, this is for sure. So, solution for system of equation, the homogeneous system, homogeneous, right. Homogeneous system, right? Okay, so in this case, so whenever you have more vectors, but lesser number of dimensions of Rn. All right. In other words, your n is larger than m. N is larger than m. What is m? M is the dimension of your vector space, not the dimension. What is this Rm? And n is the number of vectors in that. So in that case, you will have those vectors will always be what? They will always be dependent. All right. And this is the reasoning behind it. So this is infinite solution.
This is dependent or independent?
You tell me. Because it has this system of equation has infinite many solutions. So what it?
Independent.
So it should be dependent, no?
It should be dependent. It is dependent. Yes, sir. Why should it be? It is dependent. Why? Because we had noticed earlier that in the case of let's say n vectors in Rm, the linear dependency condition means unique solution, okay, of the system. But in this case, you are having infinitely many solutions. So it is not independent. So it has to be independent. All right. So what is the conclusion? Conclusion is more than two vectors in R2 are always linearly dependent. That is the conclusion. So you can also generalize this into high dimension also. Whenever you have n vectors, whenever you have more than m vectors in Rm, then they are always linearly dependent. So whenever more than n vectors in Rn are always linearly dependent. So that is what we have proved here as well. So this is the argument. Right. So this is where it ends. Now we have also used determinants, okay, to find out the solution of equations. All right, in Cramer's rule, you have seen we have used determinant to find out the solution of equation. So in this case also we can use determinant to check whether a given set of vectors are dependent or not. All right, and how do we do that? So suppose, but in order to work with determinants, what is the condition that you need? What should be the condition on number of variables and number of equations? Can anyone tell me?
They should be equal.
They should be equal. Exactly.
Because it has to be square matrix.
Square matrix.
Yes, it has the coefficient matrix has to be the square matrix. Exactly. So you guys are not correct. Yeah. Good. So in order to work with determinants, you need to work with the square matrix. In other words, your coefficient matrix has to be the square matrix, which is same as saying that number of variables should be equal to number of equations. That means n is equal to n. All right, no doubt. Good. So now we have also seen this part, that a homogeneous system of equation. Now, any homogeneous system of equation can be written as like this, okay, in terms of the coefficient matrix and the variable vector and the zero vector, it can be written as like this. So any homogeneous system of equation has a unique solution if and only if its determinant is non-zero. All right. So this is what we have seen. Let me quickly recall also. Suppose if the determinant is non-zero, that means it is invertible. So what will be the solution? The solution will be this. So x bar will be A inverse 0, which is 0. So the unique solution, it will always have a unique solution. So if it is invertible, then this is a unique solution. And if it is a unique solution, then the determinant will be non-zero. All right. So this is the equivalent condition that we have seen. Whenever you have homogeneous system linear equation having a unique solution, then the determinant of the coefficient matrix is non-zero. So now, if you want to check two vectors, if you want to check linear dependency of two vectors in R2, you just need to look at the determinant of this matrix, right? Both of the vectors. So suppose you have vectors 1, 3 and 4, 5. So you just need to look at, so it has two vectors, and how many equations will be there? There will be two equations, okay, because it is in R2. So you just need to write down. You just need to write down these vectors, okay, as columns. All right. So write down these vectors as column, and this is what we do. Now you check that the determinant of this is what?
-7.
Determinant of this -7, which is non-zero. So this is also another way to check independency, but this will only work when you have number of vectors
M equal to
number of equations. Yes, M equal to. Exactly. You can generalize this thing in the higher dimensions also. Right. So let me take an example in 2 cross 2. 2 cross 2, I have already taken an example, so let's not go there. So in case of 3 cross 3, let's say you have these three vectors, and I will ask you guys to quickly check and tell me whether these three vectors are independent or not. I will give you a simpler, I'm giving a simpler vector in R3. So you can use determinant method to check whether they are independent or not. Write each vector as a column of the matrix and then find out the determinant of the matrix. It doesn't matter whether you write it like a column or a row. It does not matter because they are all same. The determinant is same. It's a very
Independent.
Equal to 4. So independent.
Not equal to 0.
Independent
is 0.
Not equal to 0.
Not equal to 0.
Okay, you guys need to come on same page. Either some of you are doing computation mistakes. Can everyone agree that the determinant is 0 or non-zero?
Non-zero.
So -4.
-4.
-4.
Yes, sir, -4.
Yeah, so it is non-zero. So they are independent or dependent?
Independent.
Right. So they are independent. Since determinant of the matrix this is -4, they are linearly independent. All right. So, right. So you can check. So in other words, to check.
You just wrote the last determinant matrix in the column rather than in a row form rather
Right.
than a column form.
In row form. It doesn't matter. You can write it as either. You can treat vector as row vectors or you can treat vectors as column vectors.
Yes, sir. Okay.
Because
sir,
the transpose of the transpose does not change the
That's
determinant.
same.
Yes,
Yeah.
sir.
Determinant of the transpose of a matrix and the matrix is same.
Yes. Yes, sir. Thank you, sir.
So these vectors are linearly independent if and only if the determinant of writing them as column or row, whatever you like, is non-zero. Okay. All right. So this finishes off today's discussion. Now I can quickly discuss the question that yeah, I think this.
Excuse me, sir.
Yeah.
Sorry to interrupt, sir. Sir, in week 2, I faced problem in solving 4x4 matrix in the the argument matrix. Can you please tell how can I improve in that concept?
Okay, so Dilip asked me before this AQ question from week 3, fourth question. So let me first discuss that. So AQ 3.1. Consider the set V. So you guys can also help me solving this question because it is part of your activity. With the usual addition and multiplication, with usual addition and scalar multiplication. So does everyone understand what does this mean? As an good. An associated statement given below, choose the correct option. V is closed under addition. First option is V is closed under addition. Is it closed under addition?
I would have thought it is.
No, sir.
No, sir.
Why?
It is constant. 1.
Yeah, because the first coordinate.
1 becomes 2.
Yeah.
Yes.
So I would have thought the same, but then there is another example in the PDF for the same topic.
So let's take 1, 2 and 1, 3. So these two vectors are in V, right?
Yes.
But look at the sum. So their sum is what? 2, 5, which is not in V. So they are not closed.
So you don't put a condition where the first value always stays 1. So it's not going to become
There is
1.
no condition because it is under usual addition. So usual addition is coordinate wise.
Okay. So why is it that the scalar multiplication? Why is that correct then?
Why is that correct?
Yeah, I mean the third option.
Even under scalar multiplication, it's not closed.
Okay. All right.
Yeah, because if you look at the scalar multiplication, so let's say you multiply 3 with, let's say your vector 1, x, you will get 3, 3x.
Okay.
So, but this is not in V because the first coordinate is not 1.
All right. So the
now
third,
second option is BS. Yeah.
Sorry. Go on. Sorry.
Yeah. Second option says that B has no zero element with respect to addition. That is, there is no element 0 such that B plus 0 is equal to 0. Okay. So does everyone can, yeah, what is the null bit? Is there any zero element in this B? If you add that vector to this B, to any vector in B, you will get that same vector. So let's solve that. Suppose A comma B is that vector in B such that A comma B plus 1 comma x is equal to 0, 0. Sorry, not 0, 1 comma x. Right. So what it implies that 1 plus A plus 1 and B plus x should be equal to 1 plus x. Now for this first, 1 plus 1 equal to 1, B plus x equal to x. This implies that A should be 0 and B should be 0. But does 0, 0
It does
belongs
not
to B?
belong. No.
Not belong.
Yes. Why?
1 comma 0 belongs.
Yes, 1 comma, because the first coordinate is not 1. That's why it doesn't belong. Right? So second option is also false. What about the third option? Third option says A plus B times B. A plus B times B is equal to AB plus BB, where A, B are real numbers and B is a vector. Right. So, yeah. So does this satisfy? So let's check. So what is B vector 1 comma x? Let's take the LHS first and solve that. So what it will be? It will give you A plus B comma A plus B x. Right. What is this? This is A plus B, AX plus BX. All right. Now what is RHS? RHS is A1 comma x plus B1 comma x. You will get A plus B comma AX plus BX.
Yes, so that means LHS equal to RHS.
Yes, LHS is equal to RHS. So third option is correct, right?
Okay.
Right? Okay. Okay, so now next question was 4 cross 4
Sir,
augmented matrix.
excuse me, sir. Sir, I have a doubt. You had said that if it is unique, if the solution is unique, then it is dependent. But when
Independent.
we get
Independent.
determinant as -4,
Independent. 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 Not dependent. Independent.
so you had said
If it
that
is
if it is unique, then
no,
it should be dependent.
no. Look at this. Independent. Independent. I have not said independent. Independent. All right. 4 cross 4 matrix. Who asked that out? Can that person in front?
Yes, yes, sir.
Yeah. Yeah. So what was it out? Can you please articulate your?
Sir, my doubt is, sir, I face problem in solving the 4 cross 4 matrix by applying row elementary operation.
What is the difficulty? You can perform the row operations for 3 cross 3, but not 4 cross 4. That is what you're saying?
Yes, sir. Because
what is more difficult in 4?
And also like the argumented matrix.
Augmented matrix.
Sorry, sir.
Augmented
Yes, sir.
matrix, yes.
Yes, sir. I face basically difficulty in solving such question. Can you please tell how can I improve this concept?
You do more examples, solve more exercises. That's how it will improve. Look at the lecture, because I've already discussed that in the instructor session. Look at that recording of the instructor session. Look at the professor's lecture. Like, what are the examples? Do those examples which are discussed in the lecture, which are discussed in this instructor session. Do those examples and then try to do the exercise. Then you will improve. There is no other way. I can tell you one more time, but it will not help because I've already told you. So you can go back to
No,
that.
sir, not that. I watched that lecture. I was in the session too that time. No problem, sir. I will try. Otherwise, I will ask.
Yeah, if you have any specific doubt, okay, then you can ask.
No,
But
sir,
this
not
is very
like
general.
that.
Yeah. Okay then.
Thank you, sir.
Thanks everyone for joining today. Okay, I hope you have a very good night, and let's meet next time. All right.
Thanks a lot.
Thank you so much,
no
sir.
problem.
Thank you, sir.
Thank you so much, sir.
Get the notes of today's lecture.
Yeah, I will just upload in just a few minutes. Okay. See you everyone.
Sir,
So your next
so in
class is on
calendar
Sunday.
it is displayed.
Next class of this course will be on Sunday. Yes, I
So
will
what
not be
topics
taking.
are what topics are going to be discussed next
It
class?
will be week 4. Week 4. So I need to check what are the topics, but you can also check week 4 topics. It will be discussed. Week 4 we will discuss.
Okay.
Yes, Shelly.
Sir, the notes for today's class is available in calendar.
Yeah, from calendar. You will discuss.
Okay, sir. Okay, sir. Thank you.
And there is a sheet also. Google Sheet also shared with you. So the link is over there in the Google Sheet.
Sir, the Google Sheet link is in the calendar.
Yeah, I think so. That's in the. Okay. Bye everyone.
Thank you, sir.